Yeah, we're ready. So let's start. So last lecture, lecture 4. So yeah, I wanted to do too many things like other lecturers too. So I promised you for today that we would talk about recursive types, but I'm not so sure anymore if we get to it. So probably, most likely not recursive types, but I can point you to a paper where this is addressed. So instead what I want to do is I want to talk about the soundness, show you the progress and preservation theorems again, and then also show you an alternative soundness theorem where we use a big step semantics or evaluation dynamics. And then I want to talk type inference, just by example. So we look at this expansive identity function and see how we can do type inference for that. And from this example, hopefully you'll get the general idea. And then I want to show you the implementation of this automatic analysis in resource-aware ML. And I want to do the binary counter that Frank Fanning presented yesterday afternoon in the session type language. And I also want to do a functional queue, and if we have time, press first search using this queue. So, okay, that's the plan. And these examples, like the binary counter and the queue, I want to do it because multiple of you asked me, so in what sense this analysis is amortized, and these are like two classic examples of amortized analysis, and so you'll see how that works. Good, so let's start with the soundness. So what we did last time was to formulate progress and preservation, and I told you progress is not difficult to prove at all, which is true. So if we have a well-typed closed expression E, and enough potential, or enough resources, namely P, that are more than this initial potential Q requires, so then either E is a value or there exists E prime Q prime such that E with Q E prime P prime, I want to say, so that E with P resources steps to E prime P prime. Yeah, and I mentioned already that the P prime is usually just a P, except in the tick rule, where you can directly read off the type rule that you have enough resources to make a step. And so you prove that by induction on this type judgment here. So what's difficult is the preservation. So if we have a well-typed closed expression E, and enough resources available, or let's say enough resources available, and we make a step from E and P to some E prime P prime, then what? So then we want that the E prime is well typed So it should have also type tau. And what are the things I have to put here? So this is a p prime and q prime. Yeah, so and together, yeah, the theorems say kind of like if you have, you know, if you start with a resource counter that is q in your evaluation, so you pick p is q, then you run never out of resources. So you, yeah, question?
Isn't that p greater than q preservation?
Oh yeah, p greater than q. Yeah, very good, thank you. So yeah, what you don't get out of this is that like resource bounds prove termination or something like that, because yeah, they don't, right? Because you put in the ticks yourself. So if you don't put any ticks, yeah, so then you can step forever. You will not run out. Yeah, just like the resources p you started with will always remain p in the evaluation. Nothing happens. So if you wanna, I mean, you can also prove a similar theorem where you kind of like fix a resource metric and you pay for every step, right? And then you can prove a theorem that's a little bit different, where you can show that yeah, your resource bounds prove termination. Basically, I mean, you could also just do it with these two theorems, and then you would say like, okay, you have inserted the ticks so that yeah, when you start with some finite resource, there cannot be like an infinite run. So that's the only thing you would kind of like have to show, and then you also get termination out of that right away. So how to prove the preservation? So what you really want to do is an induction on the definition of the steps judgment, but this fails because we have these structural rules. So yeah, so because of that, you need to do a nested induction on both this type judgment and the step judgment. So that's the reason. But yeah, you can do that, and yeah, it's not so difficult to prove it. There are some tricky lemmas that you need to formulate. For instance, the substitution lemma only holds for values, so you can only substitute values in. Yeah, for yeah, because otherwise, yeah, if you substitute in like because you don't pay in the type system for the variables, and if you substitute something in that has some computational content or that is a computation, then kind of like it just doesn't hold. Yeah, and there are a few things like that. So the proof was a bit harder than I anticipated. There's another thing I didn't like about it. So yeah, I told you I did that for the first time last week. So another thing that I didn't like about it is because you operate on closed terms only here, there are some rules that basically don't show up in this proof directly, only in the lemmas that you use. And then I was confused multiple times, and I thought like, that's weird. So if I would just change this rule to make it unsound, where would the proof break down? And then it would be like always like in some of these lemmas that you use. And so this is another thing that I didn't like about the proof. But yeah, it works, so you can do that. So the alternative soundness theorem I wanted to show you is with big step. So yeah, recall. So this is my favorite cost semantics. So the one where you have the resource monoid. So let's say we would have defined the cost semantics like that for our language. You can also like do it with just assigning cost to these ticks, in a similar way, using this style. So then we need one short definition. So we define the potential of an evaluation environment. Yeah, remember this evaluation environment maps variables to values. So we say the potential of the environment under context gamma. Yeah, and so when I write something like that, is kind of like, yeah, okay, the context gamma assigns types to variables, and so when I write this, I mean really like the domain of the evaluation environment and the context are the same. They're the same variables in there, and they are compatible. So like, yeah, if the environment assigns a value to some variable, then this is a value of the type as defined by the context. Yeah, so they just fit together. So this is the meaning of that. So if I have such an environment with a fitting context, then I define the potential just to be the sum of the potentials of all the variables as big V as defined by the environment and the context. So it's just like, yeah, the sum of the potential in there. So, and then we can formulate the soundness. So theorem. So we assume we have an environment and a fitting context, gamma, and we have now our open term, E, of type tau, and we have an evaluation, and we have an evaluation of E to some value V in this environment, big V, P prime. So then what holds? So then the initial potential we had in our evaluation environment plus Q is an upper bound on the high water mark P. Yeah, remember this was the high water mark, and P and P prime are the resources that are available. So the initial potential is an upper bound on the high water mark. Yeah. So, and also the difference between the initial potential and the resulting potential, which is, in this value V and under tau, is an upper bound on the net cost, P minus P prime. So this is the soundness theorem that I usually have in my papers, and which was also very similar in the original paper by Martin Hoffmann, who invented this analysis. And so I want to try it out this other way, but I thought this proof here is a little bit nicer. I mean, you also have a bit of a complication because, again, because of the structural rules, you have to do a nested induction on the evaluation judgment and the type judgment, but at least if you would have like some unsoundness in your rules, then kind of like it would show up directly in this proof, and you can convince yourself, in my opinion, more easily with this proof that everything is indeed sound because it's more direct. Yeah, that's an alternative. Okay, questions? Yeah. yeah, so in both cases, yeah, but the important point here is, so what we have shown here is that, you know, we indeed achieved what our goal was at the beginning, namely that like a type derivation, yeah, this is what this shows, is a certificate of the correctness of the bound. Yeah, so this says we have a type derivation, right, and then we know exactly that, yeah, this type derivation is a proof of this bound of the high water mark. So this was, you know, the goal we wanted to achieve. Okay, good. So then let's talk about the second thing, the automation. So now, yeah, so that was not good to put it here. Let's see, because I want to do a type derivation, I need a lot of space. Yeah, let's maybe start here and then have some time to copy that. So, well, let's just say for now, oh well, okay, let's say type inference. So, before we do the inference, let's just do a regular type derivation without inferring the type for our ID function. So, how did it look again? So it was a fixed point. And then we have the pattern match. So, and then we want to have a tick maybe here, or well, maybe let's do it inside. So that's how I have it in my notes. So let's do the tick here, just before the recursive call. So okay, like this. And then what we want to derive is the following type. So when we have two potential units on the initial list and zero constant ones, then afterwards we have nothing left and also nothing on this resulting list. So this was the type we convinced ourselves that we can assign to this term. And now let's derive this. So let's call this whole type here tau ID, and let's call this function body here so this whole thing here is EID, the function body, so that I don't have to write it all the time. Okay, so now let's see. Yeah, maybe I'll write it here. So yeah, we start just with a judgment, so that we want to derive. leave out the types here in the lambda. So then we have the function body, and we want to show that this has type tau ID. So then, and I have to maybe write a little bit smaller to fit it. So then, we have to use the rule for the fixed points. What does it say? So that's okay. We can assume already that ID has this type tau ID. And oh yeah, I just realized, I don't know why I always write F here. So that's supposed to be ID. So we can assume we have this type already, and then we have to have zero potential here in the input. And so we can apply this rule only because this is a function type that has zero potential, so we don't have to erase anything. Then we have to derive a type for the function, the lambda abstraction. So, and now it gets interesting. So now what do we have to do? So we have to look at the annotation here that we want to have on the lambda, right? What's in the TID, and this is what we have to justify. So the ID remains in the context, and we get in there now also X, which has the annotation 2. Here I just write maybe 1 instead of unit to save a little bit of space. Then what do I have to write here? 0 and 0, right? Because this is what's on the arrow here. And then I have to justify that this function body has the type L0 unit. So, okay. And now we need lots of space here because this is a pattern match. So we have 3 premises. So the first thing we have to do now is, so we have the pattern match, right? So this is the E, and the X is the E, and the nil is the E1, and the cons is the E2, right? So we have to split up our context. Some goes into the some variables here can go into the E, and some can go into the E1 and E2. So what goes into the E? Well, E is X, so most likely we're going to use X. So that's pretty easy. And then, we have to feed in the potential we currently have around to pay for the E, which is 0 in this case. So this is what it says in the rule. So we have 0 here. We're going to have 0 left. And we just apply the variable rule and are done with it. So now we have to do the E1, which is nil in this case. So what we have here in our gamma 2 now is the ID. So this is what we use for the nil case. We had 0 left after the E. So this comes in here into the nil. So now we have to remember, what do we want to end up with? Well, we want to end up with 0 potential left. That's easy enough. And also 0 potential left on the list annotation. And the rule for nil says, whatever, you can put here whatever you like. So that case is also easy. So now comes the interesting part, which is the E2 here, the cons. So what do we get there? So we have still our gamma 2, which is the ID, tau ID, and then we get in addition, the y, which has type unit, and we also get the y's, which has type L2 of unit, and that's it. So now, and that's the most interesting point here. What do we have available now in terms of resources, of constant resources? 2, exactly. Yeah, why? Where does it come from? From the head, exactly. So now we have 0 left here, but we get the 2 out of the head. So we want to end up still with 0, and now here we have this cons y. So take 2 ID y's just fits, and this should have notation 0. Great. So now we have to look at the cons rule. So again, we have to split up our context. So the E1 is the y. So I would propose that we do something like this. So we have just the y. We take the potential we have and thread it through, using our relax rule here. I'm not gonna continue here, because I don't have space. But here we would use the relax basically to derive this, and then what do we have left here? So maybe I should write this here. So what do we have left? So we have the ID and we have the y's, which is a great fit, because that's exactly what we need here for the tau 2. And so what is it for the E2 in the cons, I want to say. So what is it? The tick 2 ID y's. So, and the type of this whole thing should still be L0 of 1. Sorry about that. Good. And now, here, what do we have here? Well, we have 2 left, and we want to end up with 0 still. So, and now I have to continue here. Now this is hidden for a sec. So now we have to apply the rule for the tick, or maybe let's just say continues here. We can still see it. So then we have to apply the rule for the tick. And so what does it say? We just leave the context unchanged. So we still have the ID and the y's. But now we have to subtract 2 here. And now we have the ID of y's, and our goal is still to have 0 potential on the resulting list. And now, we just use the rule for the application, because we look at the PID, right, and it's exactly what we need here. I mean, of course, we still have to, derive the types for the E1 and E2 here, but these are both variables, yeah, so I don't write it. So I'm with the application rule, right, because what I feed into the function type that we need here. So this is the type derivation. So now we want to automatically infer such a type. So how are we going to do that? So the first thing we need to do is to integrate the structural rules with the syntax-directed ones. So the first problem you have is to decide when do you want to apply the weakening, the relax, and so on. And the easiest question is you do it whenever you can. So in the implementation, I don't do it like that. I was very careful only to insert it at places where you really need it to kind of like save some constraints to make the analysis more efficient. But the easiest thing is, yeah, we apply it whenever we can. So inference. Yeah, so the first thing we need are algorithmic rules. Yeah, so this is like rules that are syntax directed. Algorithmic or syntax directed. Yeah, that's another word. So I don't want to do that in detail. I just give you an example. Yeah, how that looks. So for instance, for the variable rule, we would now say like, okay, you can have a context gamma here, so we just kind of like integrate the weakening rule into it. And if you still have some other variables around, you just disregard them. Here you can have QQ prime, and you can also just take a super type here. And so the relation between Q and Q prime is you just have to have more potential available. You can throw some out, but yeah, for instance, you can also thread something through. If you have 10, you still have 10 afterwards, but you can also say like, oh well, never mind, I only need 5 later on, I throw them out. And the same also like with this potential here, if you have a list with potential 10 assigned to each element, you can also say, oh well, I don't need that. I'm happy if I have 5 per element. So the tau prime can be a super type of the tau. Yeah, and something like that you have to do for all the rules, so that you don't have to worry about when to apply the structural ones anymore. So, and then the algorithm. So first, infer the usual types with the standard, camel or SML type inference. Yeah, so without annotations. So and the result of that is a type derivation. So now we have a standard type derivation, and we can kind of like do this here for our example. So now we forget all of those. So this is the first step. Yeah, we just use standard Hindley-Miller type inference to get something like this. So I think that's everything. Good. So then, first step already done. Great. So then, the next thing is we add to all these positions where we want to have these numbers later on, unknown variables. Yeah. Potential variables. To all or let's say potential variables where potential annotation is required. Okay, and yeah, we'll do that in a sec. And the third step is to derive, in our case, linear constraints that describe what the relation is between these variables. Yeah. On the potential variables. From the type rules. So it's basically already spelled out there in this variable rule, right? So what we gonna have in the type derivation is we have some, fresh names here, q, q prime, and then the constraint we're going to generate is that q has to be greater or equal to q prime. Of course, there's also another constraint, right, that says like, okay, we kind of like have like another rule that we applied below, which is maybe the application or whatever, and then the q that you have here on top of the turnstile has to be related to the other q you had below, so it has to be equal or at least smaller or equal to the one you had below. And so this is all there is. And then when we are done with that, we have a linear constraint system. We send it to an LP solver, and we solve it. Sometimes it's not solvable, then the algorithm would say couldn't find a bound. But if it is solvable, then we want to minimize the initial potential. I'll show you that, because in LP solving you always have an objective function, so our objective is to have as little initial potential as possible on the arguments. So let's do that here. So maybe I can use this one if it's so here. Maybe we have R0, R prime 0, and because it's the fixed point rule, it would be just something like R0 is greater or equal to R0 prime. And here, you would just have 0, so let's call it maybe R1 prime. Also because of the fixed point rule, you would there require that R1 is equal to 0 and R1 prime is also equal to 0, because you don't want to capture potential there. So the next thing you get is more interesting. What we also have to do, of course, is to fix here in this one. It's also, of course, not known yet, so we have to say here maybe we have q prime, P prime. Oh, well, maybe I wanted to do it the other way around, but yeah, anyway, now I will get confused. Yeah, well, that's fine. Well, maybe let's change it. So, because in my notes I use P here and Q there. Okay, so now here we have maybe R2 and R2 prime. So, and now so the R2 has to be equal to Q, and the R2 prime has to be equal to the Q prime. Or we can even relax it, so that depends now on like how our algorithmic rules are. We can also say, okay, we want to justify this function type. We can start with a little bit less and end up with a little bit more. That's also fine. Then we also justified it. So then kind of like, we present here at the end a type that is a little bit weaker, but yeah, why not? What else do we have here? So then the X is interesting, so let's call that maybe P1, and here the outcome P1 prime. So that also has to now relate to the thing we want to justify here. Yeah, so in principle, again, they have to be equal. So, but we can also relax it a little bit. So P1 has to be equal to P, and P1 prime has to be equal to P prime. But again, it's fine that if we start with a little bit less and end up with a little bit more, we can also allow that. And so, yeah, this is basically the idea. So now, we also want to have, here it's a little bit unusual that there's no relation between these annotations you have here on the turnstile and these, but that's just like how it is in the rules. So usually what you would have, let's maybe say this here is R3 prime. So then what you would get from the variable rule that I wrote there is that R3 is greater or R3. And now you would also get that like the R3 here has to be equal to R2. So R3 is equal to R2. And again, you could also require that it's a little bit smaller. You can have a little bit of waste there if you want. And here the same. So P2 prime. So the P2 is basically the P1. And the P2 prime is basically the P2. And yeah, again, we can be more permissive and say you start with a little bit less and you end up with a little bit more. That would be fine again. Yeah, and so on and so forth. Yeah, here, let's maybe do this one here, the cons. So that's like an interesting one. So here we basically have, let's say R4 prime. And now the R4 is interesting, right? Because the R4 has to be smaller than what the R3 prime that we had left, plus the P1 we have down there. The interesting case, and the R4 prime has to be basically to the R2 prime, right? So I think you get the idea, right? So another thing I want to show is this tick case, because that's also interesting, right? So here you have, say S1, and S1 prime. So, and here you have S2 and S2 prime. And then what you want to say in the constraints is that the S1 is sufficient to cover the S2 plus the cos2. Yeah, this is just a tick rule where you say like, okay, now you have to pay something, right? So yeah, you have to have it here, and then it goes away, and the S1 prime is basically the S2 prime. Yeah, again, you can relax it if you want. Yeah, so this is how you set up the constraint system. Then you send it to an LP solver, and what you want in this case is you want to say, so where can I write it? Everything is taken now. Maybe do it here. So this is step 4. Yeah, so solve the constraints with LP solver, yeah, off the shelf LP solver. So that's another reason why we use the rational numbers, because yeah, we can, and it's just faster than integer linear programming. And in yeah, so now we can also specify an objective function. Yeah, so the objective is basically the sum of initial potential annotations. So in our case, in the example, that would be P plus Q. So that's what we want to minimize. So in the example, maybe put it here. So minimize P plus Q. Yeah, you might say like, okay, sometimes you have the option, you can either pay for a cost with some constant or with some linear factor, and then you want to, of course, prefer to pay for it with a constant. So you can also kind of like in this LP solving, you can also have priorities. You can first say, okay, minimize P, because that's like the linear factor that we really care about, and then you can add another constraint, so then you get like a solution. You would say like, okay, the minimal thing for P is 2, in our case, and then you would add the constraint P equals 2, then you would resolve and minimize Q. And this resolving is very efficient in these LP solvers, so that's something we have in the implementation. They kind of like keep track of the path they took to minimize it. Okay, so now it's really time for a break. Questions about the inference? Yeah?
Does it mean we only have one solution about that?
No, so there are always multiple, or in many cases there are multiple solutions. So here you could also, I mean, another solution for this would be where you have 10 for P or 100 even, right? So that's why we have to say we want to kind of like have the minimal one. Yeah, but even there, kind of like there are multiple minimal ones. So if you have a function like zip, for instance, where you have two lists, so then you can assign the potential either to the first one or to the second one, or you can also have a mix. You can say like, if you have, cost 1, you can say like a half potential per element there, half potential per element there. That would also work. Yeah. Okay, good. 5 minutes break, and then we do some programming. Okay, so resource-aware ML is an implementation of that. So has a lot more features than what I was able to talk about here. So for instance, it can derive polynomial bounds, also multivariate polynomial bounds. So it can derive things like, n squared times m, where, n is the number of cons A nodes in your list if you have, cons A and cons B, let's say, in your list. So, yeah, things like that gives you an impression. But we can, of course, also do the things we talked about here. So let's implement our identity. I started already. So now we said we wanted to have a tick, and in resource aware ML that looks like this. So we have here the tick. Oh, we want to have tick 2. So tick can be a rational number, and then we want to have the recursive call here. So yeah. You saw how Frank did the implementation. So his goal is when he writes code, then he compiles, and it compiles the first time. So I don't have this goal. I wanted only to compile at the end once. So we'll see how we will do with that. So okay, so this is the implementation. So we always have to have in the end kind of like an expression that you execute, so why not put something useful here? So, okay, something like that. So then what we can do is we can evaluate it. So, okay, that worked. So the result is just, this list that we put in. Oops. Why is it making noises? And we see here, so there are 3 metrics built in. So there's like this tick metric that says like, okay, we executed 8 ticks, which is exactly right, 1 per list element. And then it also has built-in number of evaluation steps, with respect to big step semantics, and it also has a heap space metric that, we're not going to talk about today. So let's see. What else can we do? So we can analyze the code now. So I'm not sure in what mode I am. Okay, so we can analyze either just the main expression. So then we say, okay, the upper bound is 8, and it would also give us, for our convenience, just some types of the functions we used. And here you see the type of this identity, which looks a little bit different than what you've seen here in the course so far. So you see the bound seems to be at least right. So it's 2 times m, where m is the number of cons nodes. The cons nodes are written as this double colon. This is something we inherited from OCaml because we use the OCaml parser and type system. So they just call it double colon when they print it. So you were expecting to have some annotation on this list here, on this list type, but this is written down here, and this is because we have this multivariate polynomial potential. So basically we have an index system, so kind of like you have a type, and then next to it you have kind of like these indices that would tell you kind of like for like a list of unit, you would just have kind of like one index kind of like that refers to the thing that you put on the list. And if you would have like a pair of unit lists, then you would have 2 of these indices, right? But they would be written next to the type. Because now you can also have like an index for n times m and so on and so forth. So this is why it's written like that. And here this index just means exactly what you expect, kind of like for each cons node in the list. This refers to the cons you have potential to. So this is exactly what we expect. Okay. You can of course also, let's see if that works, if we apply the identity function twice. So we get the correct bound 16, and now we get two different types of ID that were used in the analysis. So we have also this new one where you have 4 that you put in and 2 that you get out. So, okay. So now, since we only have 15 minutes, I'm not sure if I can do all the coding, or if we want to speed things up a little bit. Maybe let's speed things up. So let's maybe start with the binary counter. I think we can do. So yeah, so if you remember the analysis of the binary counter from yesterday, so the idea was that we have an increment operation for a binary counter, and if you have something like 1, 0, and you want to increment it, so then it's very expensive, right? Because you have to walk over the whole list. So you do an increment, and then you end up having 0, 0, 1. But then the next operation won't be so expensive, right? So there you only do one change. And so that's much cheaper. And so if you would just do like a worst case analysis, then you would say like, okay, the cost of the increment is linear in the worst case, right? So, and then you would say like, okay, if you have n increments, so then you have something like n squared as your bound. But yeah, you can do a little bit better if you do this amortized analysis. So you would just assign a potential, to all the ones. So you would assign potential 1 here, so this is what we do, because we count, like as yesterday, the number of flips, right? And then you would say, like for the increment, you pay 2, 1 to do the flip from 0 to 1, because you exactly do 1 flip from 0 to 1, and then also 1 for the potential you need to assign to the 1. So that's exactly what we had yesterday. So let's implement that. So let's say we have a type bit that is either 0 or 1, and the counter is just represented. Why is it so weird? So we want to implement the increment, and it's a recursive function, and we get in the counter. So, and the counter is just a list. So match counter with. So if it's the empty list, then we just have 1, right? So if it and this is new. We have now this wonderful nested pattern matching, which is very nice. The same that OCaml has. So if it is 0 and some more bits, so then we just flip it to 1, right? And are done with it. Great. So, but if it's 1, that's when the trouble arises. So then we have to do 0 and have to do this dreaded recursion on the rest. Okay. So cons. Yeah. Very good, thanks. Okay, good. So this is the implementation, and so now we can analyze it. So when I switch to this module mode where we analyze every function. Oh yeah, we also should put in a tick. So we want to count each flip, but if you look at the cases, we see that we have 1 flip in every case. So here we have a flip from 0 to 1, here from 1 to 0, and here we have to create a new one. We also count that as a flip, let's say. So we just put in a tick here at the beginning. So cost 1 for every call to this inc function. So okay, and now we can analyze it. And yeah, here the type looks even stranger because it now looks like it is some quadratic bound that you get, but this is really not the case because yeah, this is just some weird notation I have because it says here L is the fraction of 1 nodes inside the cons nodes in the list. So this is just because like this type 0 or 1 is a very particular type, right? So it kind of like prints it like that because this bit type could also be a list or something like that, but it realizes, oh, okay, there are only 2 options, right? So there are not so many nodes that can be in there, namely only 1 every time. And so that's why it prints it like that. So it is, yeah, so trust me, it's exactly the thing you expect, and you can also see that here. So you have potential 1 if you have a cons that contains a 1. So basically that's what this is saying. So yeah, so you have cost 1 plus 1 for each one you have in there, and so that seems to be about right. And so now let's say, so how do I want to do that? So let's say we have some natural numbers around. So natural numbers. So, and then we want to define a function that does n increments. So if, do I even have to do it like this? Yeah, well, anyway, so let's do it like this. If, yeah, we have 0, then we just start with an empty counter and 0. And if we have the successor of n prime, then we do an increment and many increments like here. So okay, so that looks good. And we can now look at the type of the inc many, and it's exactly the bound we expect, cost 2 per increment that we do. Yeah? So 2 times m, where m is the number of s nodes, so that's exactly our number of increments that we do. So that's what we expect. So that's an example of an automatic amortized analysis. Yeah? And if you would do it naively, as I said, then you would get something that would look more like m squared or something. Yeah, but yeah, here you can do that fully automatically. So the other example is, yeah, so it's much better than Frank's language, right, where you have to annotate everything by hand. So I mean, that's a point that I have to, of course, make. So yeah, and also you get these nice symbolic bounds, which are in the session types, by the way, which are pretty hard to get only if you kind of like have a functional interface, a functional data structure at the beginning of your you have some notion of size where you can express the bounds, but if you have something interactive, yeah, then it's not so easy to even describe what a bound is. Yeah, question?
Why would you rangle block tick in the counter implementation but not in the many implementation?
Oh, just because we wanted to count the number of flips that we do. So if you, yeah, that's a good question. So what do we want to count? So you could also say you're interested in the number of evaluation steps or something like that. So we can also analyze that. Yeah, I want to show you that anyway. So steps, so I run the analysis again and count the number of steps. So then you get something that's linear in m still, which is good, but now you get some like larger numbers because you have to count like these evaluation steps. And then if you want to know how good the bound is, so you know the bound is sound, but you don't know if the bound is tight really, so you have to try it out. So let's increment a few times. 0 And I think I also have to do this. So then you can analyze it with a steps counter. So then it says like, okay, to evaluate the thing, the prediction is that it's 132 steps, and then you can run it. And you see it's a little bit off here. And the reason that it's off here is you still have this potential stored in this 1, 1 in there. So it should be off exactly. Let's do the analysis again. So we're doing the steps. So let's see what the type of the ink many is. Oh no, maybe the ink is... we don't have it here, so let's switch to the module thing. So the amount off should be exactly the potential. Yeah, was it 12 off? Yeah, that would make sense, because that's exactly the potential that is stored in this one that is still left over. It makes more sense to do this with the ticks. So when we do the analysis with the ticks, we had the potential, no, this is ID, this is ink, so we had potential 1 stored in the ones. So when I analyze the main expression now with the ticks, so I get the bound 8, and if I run it, I get the bound 7, right? Because there's 1 still stuck in there in this 1. You would only get, the worst case is basically where you end up with a list that only contains zeros, but that never happens. So you can, in this way, you can never get a tight bound unless you subtract the potential that you have left in the end. So then you would get a tight bound. But here we just report the initial potential. So it will never be tight in this case. And the more ones you have, the worse it gets, right? So if we do another one here, so then when we run it, what do we get? 8, yeah, that makes sense. And in the analysis, we get 10, right? So now we're 2 off because there are 2 ones left. So there are 2 potentials stuck there. So then the bound is off by 2. So yeah, so that's interesting. So almost out of time now, unfortunately, but I still want to show you the queue example. So I prepared it already. So a queue, so we do a functional queue which is implemented with 2 lists. So when we enqueue something, we put it into the first list, and when we dequeue something, we take it out of the kind of like we take the head of the second list. And if the second list is empty, then we copy the first list over and with append reverse and kind of like reversing it, so that like we get like the first in, first out behavior that we want from the queue. And so you are now in the same situation again, where you say like, okay, in the worst case, the cost of the dequeue is linear in the number of elements that are stored in the queue. So if you would kind of like do a naive analysis, and you would have like n NQ and DQ operations, you would say like the cost is something like n squared, but this is not true again. And you can see this with amortized analysis, where you assign potential to the elements of the first list. Where you say, okay, like when you NQ, you pay 2 or whatever. You have 1 for, let's say we count the number of cons operations. So then you pay 1 for the cons to the first list, and the other one for the potential later on when you do the copying. And you can see for each element, you only copy it over once. So you see that this kind of like will be sufficient to pay for everything. And so here, I implemented this, so it's exactly what you expect. So I count the number of cons operations. So this is why I put in a tick here, because here we have a cons, and here I have the ref append, just as you would implement it. You see that you can actually use in resource aware ML this curried style, as long as you do not kind of like partially apply your function. So this what you do here is okay. Then the DQ is where the trouble starts. So you look at the second list, right? And if you have something in the second list, so then you're good. You just return it, and the queue that you have remaining is just the one where you took out the head here of the second one. And otherwise, you have a problem when the second list is empty. So then you have to look at the first list. If that one is also empty, then you have a real problem. So then you have to say, okay, none, we don't have an element, unfortunately. And otherwise, you copy over the L1 to the list on the right-hand side, right, reversing it, and do a dequeue of that. So that's already interesting that this works, right, because it's not immediately clear that this will terminate. Even like if you would write this in a system like Cog, then you already would be in big trouble. But yeah, here you can do that, and it can prove a bound on it. So here I just implemented some test functions where you enqueue and dequeue some stuff. Let's see. So the in and out function here. So that's maybe interesting. So that takes a list L and it enqueues all the elements in L, and then it dequeues everything that was in there. So let's analyze this now. Oops, I have to switch to the module mode. So let's analyze this. Where's the in and out? Here, and you have exactly the bound that you expect, cost 2 per element that you enqueued at the beginning. So this is what we want to see. Also, for the fun of it, I implemented a press first search, which is a nice application of a queue, right? So how does it work? So I mean, first I defined a binary tree here, where I have leaves and that don't carry anything, and I have nodes that have like a payload of type alpha here, and then 2 subtrees. And so now I want to do a press first search. What do? I first enqueue the whole tree T, and then I do the following. So I dequeue from the queue, and if I don't find anything, then I'm done. If I find something, then I have a tree, and if it's a leaf, then I say, oh well, never mind, have to repeat. If it's a node, then I look up if X is the element I'm looking for in my search function, which is F, which I got in here at the beginning. So if I'm happy, if this is like true, then I return it. Otherwise, I recursively call this press first search, and I enqueue the subtrees. So this is a very nice way to do the press first search on a tree. And so I can also analyze this function. So where is it? BFS here, and I get this linear bound. Well, but we only account for the queue operations here. So you might also ask, like, okay, what if we do the evaluation steps for this one? So then you also get a linear bound, and this is what we want to see, right? Because if we would do it naively, then with all these like enqueues, we would get something quadratic in the end. So so these are the kind of like things you can implement. So maybe there are some questions. Otherwise, I can tell you also a little bit more.
What happens if you write something that doesn't?
If you write something that so that's also something we learned from Frank yesterday. We should do something that kind of like fails. So here, let's say we just use this old queue that we have around. So then this shouldn't work. So let's do evaluation steps. So where's this BFS? So then what it would say is like, okay, a bound for BFS could not be derived. The linear program is infeasible. And then you don't know really, is it because there is no bound, or because, I mean, it's an undecidable problem. It could also be that just like the system is not powerful enough to find a bound. So there are, here in this case there are no tricks really that you have to do, but sometimes it's just, yeah, for instance with this capturing of potential from the environment. Oh, there's one trick you can see, so that's probably a good one. So let's fix this first. So let's see if it works now. Oh, doesn't work still. That's a bit surprising. OPLSS. So
If you added the quote in the last queue in the register function, it's still the old queue. Like,
oh, yeah, very good. Yeah, so no, I still. Yeah, so this is something that's also interesting. I mean, if you have this functional queue, you have to use it the right way. If you kind of like use one version of the queue twice, then all bets are off. So that's also something I want to show you, because then you have to do maybe this expensive operation twice, and then this whole potential reasoning doesn't work anymore. So here, this only works out with the sharing, right? Because we never have to do the sharing. So this is why this whole thing works. But that's only a side remark. So let's do the analysis of the BFS again. Okay, so now we're good again. So now I show you the trick I had, but then I also have to do changes. But yeah, well, anyway, so I have the empty queue here unnecessarily has this unit argument to make it a function. So if I don't have that, then we get a problem here. Why? Because we are trying to capture potential. So let's see what happens. So my guess is it will fail now. Yeah, I see already a lot of, yeah, doesn't work anymore. Because now, even though you have just these two empty lists, they don't really carry any potential. But the system doesn't know that. It would just say like, oh, well, this annotation on this list has to be 0, but you need it to be more here so that it works. So that's like a typical pitfall where you then like say like, oh, well, why doesn't this work? And you can spend a nice afternoon trying to find the error. So it would be really nice to have better error messages than bound couldn't be derived, but it's not so easy to do when you have this constraint solving. So yeah, that's a bit of a challenge, right? And maybe I show you one example. That's the last thing. So which one? Maybe quick sort. So just, oops. What's the problem with this file? Okay, let's do another one. Insertion sort. So just to show you like how a more complex bound looks. So this is a bound for insertion sort for lists of lists, yeah, where the each comparison takes linear time. So then the bound is something like, m squared times L, where L is the maximal length of the inner lists, because you do m squared comparisons, and each comparison takes linear time in the size of the inner lists. Yeah, so then you get a bound like this, but yeah, these are the things you can do in resource aware ML that also work. So this is kind of like very expressive, but you cannot do things like logarithmic, for instance. So that's a limitation. Okay, so now already more than 10 minutes over. So that's it. Questions offline. Thanks.